Okay, so many thanks for the invitation to speak in this African mathematics seminar. As I said, I'm speaking to you really from my kitchen in a quite chilly Copenhagen. I wish I was in Africa right now, but in some sense I am, thanks to the wonder of digital electronics and communication. So my talk today is called Applied Mathematics Applied. And as Marty said, I'm from the Technical University of Denmark, the Department of Applied Mathematics and Computer Science. But before I dive into the description of study groups, I will say a few general things about my thinking about this as a broader concept, because I believe this is an all mathematics series of seminar, and not just for applied mathematicians. And where do we stand on this issue between the real and the abstract? Well, there's this wonderful metaphor, which is, I believe, 2,500 years old, give or take a few, given to us by Plato, about the idea that the things we are seeing, like the chained prisoner looking at the wall on the right of this picture, is just a reflection of perfect things from a flickering light of a flame, and that the mathematical ideas really belong to some abstract realm, and then they can be more or less represented in the natural world. And there's a whole long discussion, which I'm sure all of you have been involved in from time to time, is whether mathematics is discovered or invented. And this can get mathematics or mathematicians talking for a long time, and I won't make any big discussion into this, except to say I think somehow the question is too much a dichotomy. It looks like you have to choose between the two, and I think there's a huge gray zone in between. But for sure, at one extreme end, a mathematical statement like this is a discoverable fact. It's something which is true independent of whether there's anyone around to see it. It is simply true, and you can discover it or not. So you don't need any people to or any intelligence to notice that this is true. But then on the other hand, something like this is much more subtle and has much more the character of a construction. Something where you have to know infinite series and arrive at the Riemann conjecture and make analytic continuation and so on. So there's certainly a spectrum between things that are discovered and things that are questions that are invented, of mathematics that are invented. And this, it leads to sometime to a division between pure mathematics and applied mathematics, where in my opinion, the two are connected, just like the roots of a tree and the leaves of a tree, and a higher standard of living. And mathematics contributes significantly to the economic welfare of nation states. Here's, for instance, an interesting figure from the Dutch report in 2014, where, so on the x-axis is an indicator of the sort of the effort, the national effort on educating young people in mathematics, the infamous notorious PISA mathematics score for schools, and on the y-axis is a measure of the competitiveness of the economy. And there is a correlation, and you can ask, what are the nations here at the very tip? These are nations like Korea, Taiwan, and Singapore, where we know that they make a lot of effort in mathematics. So this contribution to mathematics as a contributor to the competitiveness and the productivity of the economy is often overlooked. And in fact, you know that people tend to overlook the contribution of mathematics to even things like computing. Here's an example. Are you seeing this? The famous law of Moore's law for the output of computer chips. And you can ask, what does that have to do with mathematics? Well, not immediately, but the point is that there's another law, namely for software and computational algorithms, which mathematicians very much contribute to. And so the speed of algorithms alone is also increasing logarithmically, just like Moore's law. And the two together really is what are making computation so efficient. If we didn't have this constant increase in clever and sophisticated algorithms, but were just relying on computer chips, we would be computing somewhat like we did in the 90s or so, with the speeds we had in the 90s. But fortunately, both the processing power of computer chips and the secret power of mathematics inside the computer chips give us a huge advantage. And as it says here, these effects strengthen each other. So now I'm beginning to approach the central topic, namely that even though mathematics has a tendency to evolve into highly specialized fields, when it comes to interacting with society, a key role has emerged for mathematicians who have sort of one foot in each camp, who understands both the real world situations and also is roughly familiar with the many abstractions that can be brought to bear on tackling problems. Because there are so many mathematical disciplines. And so not only do you need mathematicians who are well-rounded, but in fact, you need cooperation among many mathematicians, groups of mathematicians to join together and help each other to solve problems and connect not just across disciplines, but also across nation-state borders. And I know the fact that I'm speaking here in this all-African seminar is an example that this is happening in Africa, and it is certainly also happening in Europe. As Matti mentioned, I'm involved, and Matti himself was one of the founding fathers of the so-called European Consortium for Mathematics in Industry, which is a loose connection between universities and institutions that educate coming generations of applied mathematicians, and generally have a lot of activities. I invite you to look at this webpage, where you can see that we support both research and education, and there are many applications. There's a conference coming up next week. And then there's a button for study groups. And this is what I wanted to get to here, the study groups with industry, which is a regularly occurring thing these days, but it began back in the 1960s, I believe, in Oxford, as an event where academic mathematicians would get in touch with companies and accept what they call challenges from companies to see if they could actually do mathematics to solve some of the issues of modeling or computation that various companies were facing. And this took on the character of a regular and annual meeting, and it began to spread across the UK, and later it began to spread across other European countries. And these days, at least this is a pre-pandemic number, It was up to about 5 to 8 different events every year, spread across all the various countries of Europe, and in fact across the world. And there's a regularly occurring study group in South Africa that I know of, the MISGSA in South Africa, organized by David Mason at WITS, and they just had one of these meeting a few weeks ago. And what is it? Well, it's as I mentioned, it begins with various companies. So you see here companies to the far right who have posed questions to academic mathematicians or applied mathematicians at universities. And then in the span of 1 week, these mathematicians provide answers back to them. I say answers deliberately because it would be a little bit bold to say solutions at this point, because there's a limit to how much you can do in a single week. But still, the concept has proved so popular over the years. It has now been going on for 50 odd years. And this is, in my opinion, because it has the character of a win-win situation, where the companies have their problems, if not solved, sometimes solved, but certainly discussed among independent experts or impartial experts in the course of a single week. And this can mean a lot to companies to have educated specialists look at the issues of modeling or computation that they have. And on the longer run, they establish contacts with academics, and often students are involved, and students can come work at the companies. From the point of view of the academics, there's the always pressing issue of, if you're so smart, why don't you test your skills on real world problems? And this is an opportunity to do just that, to see if you are really in touch with things that are actually occurring in everyday life, like you tell your students that you are. And you also, from these workshops and this brainstorming, you get new ideas for your own personal research and teaching. I have had many exam questions that originally came from these workshops with industry. And of course, on the longer run, also the contact to companies where students can do projects and sometimes get employed is a good thing. So there is this back and forth between what you would call the ivory tower, the isolated, quiet hallways of a mathematics department, and the noisy environment of the factory floor, where I think it's a healthy going back and forth. And this mutual exchange of issues and questions and solutions and answers has been very helpful. One thing is, it has to take place during a single week. I mean, there are many other formats there's something called the industrial PhDs and master projects that can be done in relation with companies. But these workshops have an urgency to them, which is really inspiring, and you have to participate in one to really get the idea of this type of effort. So the format is really simple. You set aside a week, and on Monday morning, the companies each one by one present their problems and issues and challenges, and then the assembled mathematicians get together and divide into groups, one group around each problem, and then they just work hard and eat and sleep from time to time, but not too much. And then on Friday, each group presents back to the companies their solutions or considerations, how far they've gotten during the week. So I'm counting on you alerting me if suddenly the page turns blank or something. But I had to show you this picture. So this is Professor Please from Oxford, and this is an earlier, also pre-pandemic me. And what is going on in this session is that we are trying to get our heads around specific problems. And it is a bit like the metaphor with the elephant and the blind men, where the mathematicians coming from one area thinks that the problem has to be addressed within their area. Some will say this is clearly a linear algebra problem, whereas other mathematicians will say, no, this is a graph theoretical problem, and you have to. And this discussion and this interaction is extremely both entertaining and also useful. So in the remaining minutes here, I will try and give you 3 examples of study group problems that we have done here in Denmark. So I've personally participated in study groups in many countries, India. So I'm picking 3 examples of study group problems in Denmark. So my first example is from a small company who studies the so-called bearing capacity of roads. And I confess, I had no idea what this was about before we interacted with this company. It turns out for paved roads, you can judge the age and the quality of the road by the way in which the road gives slightly underneath the load of a heavy wheel. This has been known for a long time. So this has to do with the property of some asphalt and bitumen. And the more it gives generally is a sign of weakening of the road. And for road authorities who maintain the roads, it's a question of knowing early when this sets in, because the earlier you fix a road, the less the overall costs will be, because it becomes non-linearly more expensive to fix a road that is deteriorating. Okay, so this company invented a very clever concept which involves Doppler shift lasers. So these Doppler shift lasers can detect via some integration procedure minute changes, and this figure here is wildly exaggerated. So these lasers give you super accurate information of the way the road gives underneath the wheel of a truck. But what they needed from us was a small, a low parameter model for the road, which they could compare their data to. So they had more data than they had useful modeling. So they needed some simplistic modeling from our part. And this we were able to give them. And in fact, if you can just make out the green curve down here is now a part of the company logo, which you can see on the side of the truck here. So we pride ourselves, and we were helpful in helping this small high-tech company develop their product. And we are still in touch with them, and they still give us problems for the Danish study groups. So the second problem I wish to have is from a huge pharmaceutical company in Denmark called Novo Nordisk. I think the main product is insulin, and they produce a significant fraction of the insulin to diabetic patients on the planet. But they also have research in many, many areas of pharmaceutics, and they are even at the point where they are sort of studying a large class of chemical substances for use in medicine. And these substances have to do something with the cells of living organism, and in particular, they have to activate receptors on the cell surfaces. And if you know what you're doing and you know the cells, then you want your substance to touch the cell in some spots and not touch the cell in other spots. And this is what is illustrated in this figure. So these molecular pharmaceuticals must connect with the cell surface in some spots and avoid other spots. And then you can ask, can you systematically search in organic compounds for molecules who can do just this particular trick? And this, of course, is an issue in graph theory. So you can ask how many graphs of reasonable simplicity and connectedness have the property that they go through these vertices and not go through the red vertices. And what is reasonable here? Well, they have to be able to synthesize it, and since most of these substances are organic, they have to have a shape which is more or less can be fitted maybe on an hexagonal lattice or a diamond lattice. So this was the more specialized question they gave to us, and we thought about it for some time, and then we were fortunate enough to have people from topology optimization, people who had designed wings on the Airbus using topology optimization. But topology optimization can also be made to work at the molecular level. And the codes that they used to systematically search in a kind of shape space were brought to bear on this. And it turned out to be a wonderfully efficient way to sort through potential molecules. So it was even considered for a time that we should take out a patent in this, but fortunately for us, and maybe also for Novo, we agreed with them that we should simply publish it, and so we didn't take a patent to this. But it ended up in a publication, as many of these projects do. So everybody was happy. Novo was happy. The involved scientists were also happy. Okay, so are people still seeing my screen? So I'm down to my last example here, and my last example, I cannot help but I have to bring this, is from Lego, another well-known global Danish company, and they had a wonderfully puzzling and simplistic question for us, namely how to build with Lego bricks. And first we asked them, don't you know, of all people, how to build with Lego bricks? But it turned out their question was quite a bit more sophisticated. And this has to do with the issue of whether the construction of some Lego construction is optimal. As it was then, and probably is now to some extent, is that they have a human person involved in making this Lego construction, whether it be a spaceship or a boat or something. The instructions that you see in a Lego kit is made by a person who has put it together from...
Poul, your screen has frozen again.
Oh no. Oh no, do we have a few minutes? I'm almost done, but I guess I have to restart here. So, are you seeing this?
Yes.
Good. Lego, how to build with Lego bricks. How much of my explanation did you hear? So Lego essentially asked whether you could, if you knew the shape of your Lego construction, convert this shape to an optimal algorithm so that there was no question that the building instructions that you put out in the Lego kit is optimal. And optimal here means that you're using as few bricks as you can get away with, while still maintaining some structural integrity of the Lego constructions, because if you build it, the whole thing with one by ones, it is not sturdy at all. So you need a maximum amount of overlap between the Lego bricks, but you still need to use as few Lego bricks as slide here. The Lego problem. So it's an example of a problem which we really couldn't solve to our satisfaction, at least. It turns out to be one of these problems which is really, really hard, much harder than playing chess, is to build even simple Lego constructions in an optimal way. Since this was back around the turn of the millennium, a lot of people have continued working on this Lego problem, and they have found partial solutions which are near optimal, certainly much better than just guessing to this problem. And it all began as an innocent question to a study group with industry. And it's one of these examples where the arrow goes the other way, where an attempt to solve a very practical and straightforward problem in industry turns out to generate a lot of academic activity that may end up in other places than just Lego bricks. For instance, the whole concept of optimal construction of a shape by layer is relevant for 3D printing. So this was my third, and I think I should stop here, final example of study group problems. So just returning to my initial slides, I wanted to emphasize that sometimes real world questions can feed back on the so-called pure mathematics and invigorate pure mathematical research. So a few minutes late, thanks to a not so helpful technology, I'm at my conclusion, namely that there's an emerging trend in applied mathematics and industrial mathematics, where collaborative mathematics give this connection between pure academic, the ivory tower, and the factory floor, which has enormous impact and a great amount of stimulus at each end. And so with this, I will finish my talks.